magnetic domains. By the end of this section, we're going to really understand how an iron works and why is iron and cobalt attracted to a magnet. Permanent magnets are made by simply placing pieces of iron or certain iron alloys in strong magnetic fields. Alright, so we have the magnetic fields of individual iron atoms are strong. Interactions, remember where that magnetic field within the atom comes from, that spinning electron. Interactions among adjacent iron atoms cause large clusters of them to line up with one another. In this context, adjacent just means next to or touching. So the interactions between the touching atoms cause these magnetic fields to start lining up with one another. These clusters of aligned atoms are called magnetic domains. Each domain is perfectly magnetized and is made up of billions of aligned atoms. The domains are microscopic, and there are many of them in a crystal of iron. A mag strip of a credit card contains millions of tiny magnetic domains held together by a resin binder. Data are encoded in binary with zeros and ones distinguished by the frequency of domain reversals. So that's how, when you swipe that credit card, or used to swipe the credit card, how the computer knew which bank to ask for the money from. The difference between a piece of ordinary iron and an iron magnet is the alignment of the domains. In a common iron nail, the domains are randomly oriented. When a strong magnet is brought nearby, there is a growth in size of domains oriented in the direction of the magnetic field. So you have all of these magnetic domains just all over the place. And then when you bring a magnet nearby, those domains start lining up with each other. So they're in line with each other, and because of that magnetic field from the atoms not being canceled out, that's what allows for the attraction of the iron nail to the magnet. The domains also become aligned much as electric dipoles are aligned in the presence of a charged rod. When you remove the nail from the magnet, thermal motion causes most of the domains to return to a random alignment. So as soon as you pull that magnet away, then the electrons are going to continue to spin and rub against each other. The atoms are going to rub against each other, and you're going to get some of this thermal energy. And as that happens, then the domains just become separated again. Permanent magnets are made by simply placing pieces of iron or certain alloys into strong magnetic fields. Another way to make a perfect magnet is to stroke a piece of iron with a magnet. The stroking motion aligns the domains of the iron. If a permanent magnet is dropped or heated, some of the domains are jostled out of alignment and the magnet becomes weaker. The arrows represent domains where the head is a north pole and the tail is a south pole. Poles of neighboring domains neutralize one another's effects except at the ends. So here we have the unmagnetized iron, and you have the domains just all over the place. Then, maybe there's a magnet nearby. Okay, it's slightly magnetized. We're starting to see some uniform direction. Most of them are pointed towards the North Pole. And then, when there's a strong magnet present, then you're going to get this perfect alignment, and it's a good, strong magnet that you've created. If you break that iron bar magnet in half, then remember, we have a North Pole and a South Pole, and a North Pole and a South Pole always. Think about this. Iron filings sprinkled on paper that covers a magnet were not initially magnetized. Why then do they line up with a magnetic field or the magnet? What do you think? Domains align in the individual filings, causing them to act like tiny compasses. The poles of each compass are pulled in opposite directions, producing a torque that twists each filing into alignment with the external magnetic field. So they're all just like these tiny little compasses, all of those little flakes that we've seen. Concept check. You should be able to answer this by now. How can you make a permanent magnet?